Deep Q networks or DQN. DQN is a reinforcement learning algorithm that combines Q learning with deep neural networks. It uses a neural network to approximate the Q values for each action in a given state, allowing it to handle environments with high dimensional and continuous state spaces. DQN uses experience replay, storing past experiences and training on random batches, and a target network to stabilize training. Let's look at line by line implementation for DQN. So I'm going to go ahead, start with an empty file, deepq networks. First, let's import our libraries. So I need import gym. Now gym provides the environment interface for reinforcement learning. Example, in our case, we're going to use cardpole version 1. Next, we'll need torch. We need torch nn, and we'll need torch optim as optim. So PyTorch libraries, these are the PyTorch libraries that is used to build and train the DeepQ network, which is DQN in our case. Next, import NumPy is used for numerical operations, especially for arrays and converting data formats. Then we're going to import random. Now this is Python's random library used here for sampling random actions and selecting batches from the replay buffer. Next, let's go ahead and define the DQN model. So for DQN model, I'm going to say class DQN and pass nn module as a parameter. This DQN class inherits from nn.module, making it a PyTorch neural network model. So first thing that I need is initialize the DQN model with 3 fully connected linear layers. So that is, I'm saying def the function in it with self, input size, and output size. So for this, I'll add self. First, I'll call the super method. Then I'm going to say self.linear 1 equal to nn dot linear input size of 64. This is the first layer that takes input size, which is number of state features, as the input, and output 64 features. Next, I'm going to say self.linear equal to nn dot linear 64 by 32. This is the second layer, processes the 64 features and outputs 32 features. And then I have self.linear 3. This is the final layer that outputs output size values, 1 for each possible action. So that's how you initialize the DQN model with 3 fully connected layers. Next, let's create the forward method that defines the forward pass of the model. It applies ReLU activation to self.linear1 and self.linear2 layers, and no activation on the third layer or the final layer is needed as it outputs Q values directly. Next, let's define the hyperparameters. So for this, I'll have the different hyperparameters including environment name, which is cardpole v1, which specifies the gym environment. Next, I have the learning rate of 0.001, is the learning rate for the Adam optimizer. I need a gamma, which is the discount factor for future rewards. I'll use a buffer size, which is the maximum number of experiences to store in the replay buffer. I'll need a batch size of 32, which is the number of experiences sampled from the replay buffer per training step. Need epsilon 0.1, which is the exploration rate for epsilon-greedy action selection. And then I'll need the target update frequency, which is number of steps between target network updates. So next thing that I'm going to do is I'm going to initialize environment and DQN model. So I'm going to say here env equal to gym dot make env name. Now env creates the gym environment specified by the environment name. Next, I'm going to say input size equal to environment dot observation space dot shape 0. What it does is it sets the input size for the DQN model based on the state dimension here, and then output size equal to environment dot action dot space dot n underscore space dot n, which sets the output size for the DQN model based on the number of possible actions. Next, I need the device equal to torch device CUDA if torch.CUDA is available, else CPU. This sets the competition device, either GPU if it's available, other CPU. And since I'm learning on my local laptop, it's going to just use the CPU. Next, policy net equal to DQN, input size, output size to device. This is the main DQN model for action selection. Next is my target net. This is a secondary DQN model used to compute target Q values and updated periodical for stability. Next, I have target.net load state dictionary. So what this does is initializes target net with policy nets widgets. That's why it says the parameter that is passed is policy net dot state dictionary. Next, I'm going to say target underscore net dot eval. This puts target net in evaluation mode, disabling gradient updates for stability. Now let's go ahead and create the optimizer. Optim add dot addum policy net dot parameters and LR equal to learning rate. So I'm passing those. So this creates the addum optimizer for updating policy nets weights. So next is criterion nn.mse loss. So this is mean squared error loss for training, which measures the difference between the predicted and the target Q values. Next, let's go ahead and add the replay buffer. So I'm going to create a experience replay buffer equal to empty. This stores past experiences for experience replay. Experiences are tuples of, it contains state, action, reward, next state, and done. So let's go ahead and run the training function. So this is our training function that trains the agent over a specified number of episodes. I'm going to set the step count equal to 0, which keeps track of the total steps for the target network updates. We're going to use probably like around 1000. And then let's go ahead and run the episode loop. So what I'm going to do here is I'm going to say for episode in range, depending on number of episodes that are passed to me. So this loops through each episode for training, and it will set the state underscore equal to environment reset. This resets the environment at the start of each episode. Next, I'm going to say state equal to np.array state. This ensures state is the numpy array for later conversion to PyTorch tensors. And then I'll have my done equal to false, where what this does is this initializes the done flag to keep track of episode end. I'll have total reward equal to 0. It accumulates reward per episode. Next, I'm going to say while not done, this is the inner loop where the agent interacts with the environment until the episode ends. So let's go through the episode. So this is the epsilon-greedy action selection. So for that, I'm going to say if random.random is less than epsilon, action should be environment.action underscore space dot sample. Else, in the other case, like so, first with probability epsilon, choose a random action. Otherwise, use policy net to choose the action with the highest predicted Q value. So that's what this does here. It will, so you have specified action equal to policy net torch.tensor, pass the state, give the d type equal to torch.float, device equal to device, and argmax item. So this will take care of that. Next, let's take action and observe reward and next state. So in this particular case, so I'm going to say next state, comma reward done truncated underscore equal to environment step action. This takes the selected action, receiving the next state, reward, and flags for completion. Then I'll do done equal to done or truncated. This sets done to true if either done or truncated is true, ending the episode if the agent reaches the goal or the time limit. Next, I'm going to say next state equal to np dot array next state and pass the total reward equal to plus equal to reward. This updates the cumulative reward for this particular episode. So that's what it happens here. Now next, I'm going to go store the experience in the replay buffer. So for this first thing, I'm going to set the replay buffer dot append state action reward next state and done. What it does is it adds the experience to the replay buffer. Next, I'm going to say if length of replay buffer is greater than buffer size, then remove the oldest experience. So that I can do by saying replay buffer pop 0. Next, I'm going to say state. So now I'm going to update the state equal to next state. This update stage to the next state for the next step. So let's go ahead and for experience replay and training, let's sample a batch from the replay buffer. So I'm going to say if length of replay buffer is greater than equal to batch buffer, batch size, What this does is it ensures enough samples in the replay buffer before training. Then I want to do is batch equal to random.sample. This samples a mini batch from the buffer. Next, I'll say states, actions, rewards, next states, done's equal to zip star batch. What this does is this unpacks the batch into separate components. So once that is done, I'm going to convert these batches to tensors. To do that, I'm going to say state equal to torch dot tensor states d type torch dot float and device equal to device. So this will convert each batch component to a PyTorch tensor of the correct device. So for this is for states, then I'll do for the action similar stuff, I'll do for rewards, I'll do for next steps, and then for done's I'll do this. So I have all these different ones converted the batch to tensors. So that's why you use torch tensor. Next, I am going to compute the Q value and the target Q values. To do that, I'm going to say current Q values equal to policy net states dot gather 1 comma action unsqueeze. This computes Q values for actions taken using policy net. And then next Q values, target net. So this computes the Q values of the next state using target underscore net. And then target underscore Q values is rewards plus gamma times next Q values times 1 minus done's. So this calculates the target Q values based on rewards and future Q values accumulating, accounting for episode termination. So that kind of brings us almost close to the end, where next I need to probably go ahead and optimize the model. So I'm going to compute loss and update the policy network by saying loss equal to criterion current Q values target Q values dot unsqueeze. This calculates MSE between current and the Q and the target Q values. Then I'm going to say optimizer dot zero grad. This clears previous gradients, and then loss dot backward. This computes the gradients and finally update the model parameters using optimizer dot step. Now let's go ahead and finally update the target network by saying update target network step count plus equal to 1, and if step count mod target update frequency equal to 0, target dot net target underscore net dot load state dictionary policy underscore net dot state dictionary. What this does is this updates the target net periodically with policy net weights for stability. So that's what happened here. Now finally go ahead and print the episode and the total reward that is got, and now that we are ready, we can just go ahead and run the training. So I'm going to say train number of episodes equal to 1000. You can reduce it just to check for a quicker, but I'm going to run it for a little while so it reaches its destination very easily. So I have all the code ready now here for our DQN or DQ networks algorithm. Next step is to run this. So let's go ahead and say Python DQ network, and it's going to start running, going through each episode and then calculating the total reward. I'm going to give it some time because I said 1000 and I'm at like 160 right now. I'll come back in some time and continue with this. So it took some time and it completed our entire code, and it has trained our network, and we have a model available to use. So that's your DeepQ network algorithm, and that's how you can use it. If you had any issues or problems implementing this, let me know in the comments and I'll get back to you.